This presentation provides an overview of a 2-year research study conducted at the University of Kentucky examining the effectiveness of soil solarization as a management tool for soil-borne pathogens in high tunnel production systems. This work came out of repeated conversations with growers asking the same basic question. Can solarization actually work here in Kentucky, and can it work consistently enough to rely on? This study focused on 3 economically important pathogens: Agroathelia rolfsii, the causal agent of southern blight; Fusarium oxysporum, the causal agent of Fusarium wilt; and Rhizoctonia solani, the causal agent of Rhizoctonia, crown, and stem rot. These organisms are known for their long-term persistence in soils and are some of the most frustrating pathogens to manage in protected production systems. Because fungicide options are limited, especially in high tunnels, growers are often left needing reliable, evidence-based alternatives. Soil solarization has long been promoted as a non-chemical option for reducing soil-borne inoculum, but its performance in temperate regions like Kentucky hasn't been well documented. High tunnels offer a warmer, more controlled environment, so the question we wanted to answer was whether solarization in closed high tunnels could consistently reach temperatures high enough to reduce pathogen viability across seasons and soil depths. Soil solarization is a non-chemical technique where moist soil is covered with clear plastic to trap solar radiation. When conditions are favorable, this method increases soil temperatures to levels that can reduce or kill heat-sensitive pathogens. Solarization is widely used in hot, dry regions, but its effectiveness in temperate areas like Kentucky has been less clear. High tunnels offer a potential advantage by creating a warmer and more controlled environment, so we set out to evaluate whether solarization within high tunnels could reach temperatures high enough to achieve meaningful disease suppression. In 2024 and 2025, we conducted solarization trials in a closed high tunnel in Lexington. We evaluated solarization in spring, summer, and fall each year. Plots were either left uncovered, covered for 2 weeks, or covered for 4 weeks. We buried fungal pathogens in mesh packets at depths of 2 inches, 4 inches, and 6 inches. Soil temperatures were monitored continuously at each depth, and after each solarization period, the packets were recovered to determine survival. The soil temperature data revealed a very clear pattern. Solarization performance depended strongly on both the time of year and the depth at which fungi were buried. This graph illustrates temperature changes over the course of a day, averaged over 4 weeks and 2 years. Temperature is shown on the vertical axis in Fahrenheit, and time of day is shown along the horizontal axis. Soil depth is indicated by color: blue for 2 inches, red for 4 inches, and yellow for 6 inches. A few things are immediately apparent. Temperatures were consistently higher under solarization. Temperature fluctuations were greatest near the soil surface. You can really see that in the blue line. And the highest temperatures occurred predictably in the mid to late afternoon, usually around 3 to 4 p.m. During the spring, even under plastic, temperatures at 2 inches only reached about 95 to 104 degrees Fahrenheit. Temperatures at 4 and 6 inches stayed below 95 degrees. These temperatures are generally not high enough to inactivate most soil-borne pathogens. Summer, on the other hand, produced consistent and biologically meaningful heating. At a depth of 2 inches, solarized soils exceeded 100 degrees, with extended periods above this threshold and many hours suppressing 110 degrees, approaching or meeting temperatures associated with pathogen death. Temperatures at 4 inches also climbed above 100 degrees, though peak values were lower and less sustained. At 6 inches, temperatures remained noticeably cooler and seldom exceeded 100 degrees. Even during peak summer conditions, lethal heating was largely confined to the upper soil profile. As with spring, higher temperatures occurred under solarization, and the highest temperatures occurred later in the afternoon. Fall temperatures were intermediate. In most cases, only the top 2 inches briefly exceeded 100 degrees, while deeper soil layers remained comparatively cool and far below lethal thresholds. The same overall temperature trends observed in spring and summer also held true in the fall. Overall, these temperature patterns showed that meaningful heat accumulation in Kentucky high tunnels occurred primarily during midsummer. Pathogen responses closely mirrored these temperature trends. In these graphs, percent survival is shown on the vertical axis, while season and treatment duration are shown on the horizontal axis. Solid bars represent solarized treatments, and striped bars represent non-solarized controls. Rhizoctonia solani was the most heat-sensitive pathogen in this study. In spring, solarization reduced survival by roughly half. In midsummer, solarization completely inactivated Rhizoctonia at all three depths, 2, 4, and 6 inches, with no surviving inoculum detected. In fall, reductions were observed, but they were not as consistent or as complete as those achieved during summer. Fusarium oxysporum showed moderate heat tolerance. In spring, solarization had little effect. In summer, survival at 2 inches often dropped to near zero, and noticeable reductions occurred at 4 inches. At 6 inches, nearly half of the inoculum survived in 2024, while about a third or less in 2025. In fall, only slight reductions were observed. Agroathelia rolfsii was the most heat-tolerant pathogen in this study. In both spring and fall, solarization had minimal impact. In midsummer, survival was significantly reduced at the 2-inch depth and was occasionally eliminated entirely. However, at 4 and 6 inches, survival remained moderate to high even under the highest temperatures observed. Taken together, these findings can give us some clear and practical guidance. First, solarization in Kentucky is most effective when done in midsummer, particularly in July, when temperatures inside closed high tunnels are highest. This study only evaluated solarization in July, so June and August were not included, but may have high enough temperatures to be effective. Second, solarization has its greatest impact in the top 2 to 4 inches of soil. Temperatures at 6 inches were not consistently lethal, even in summer, which means deeper inoculum is likely to survive. Third, pathogens respond very differently to heat. Rhizoctonia solani is highly susceptible and can be effectively eliminated with midsummer solarization. Fusarium oxysporum can be significantly reduced, especially near the soil surface, but complete elimination is unlikely. Agroathelia rolfsii is the most difficult to control, and only shallow sclerotia are likely to be affected. Finally, solarization should be viewed as one piece of an integrated soil disease management strategy. Even when temperatures are sublethal, it can still provide meaningful reductions in pathogen pressure during a crop-free summer window, especially when combined with crop rotation, sanitation, organic amendments, and biological controls. In summary, midsummer high tunnel solarization in Kentucky can be a useful tool for reducing specific soil-borne pathogens, particularly in the upper soil layers. Its effectiveness is limited by season, soil depth, and pathogen biology. But when timed correctly and integrated with other management approaches, solarization can play an important role in improving soil health and reducing disease pressure in high tunnel production systems.